Chapter 5 Prime Time Common Multiples and Common Factors. It's an Idli-Vada game. Children are sitting in a circle and playing the number game. One of the children starts by saying 1 and the second player says 2 and so on. But whenever it comes the turn of 3, 6, 9, that means multiples of 3, that player should say Idli in place of number. And whenever it comes the turn of 5, multiples of 5, 5, 10, 15, 20, etc., that player should say Vada instead of that number. When a number is both a multiple of 3 and a multiple of 5, the player should say Idli-Vada. If a player makes any mistake, then they are out. This continues in rounds till only one person remains. So we can write the multiples of 3. Here multiples of 3, that means multiplication table of 3. We know that 3 1s 3, 3 2s 6, 3 3s 9, 3 4s 12. So we can write the numbers whatever it comes in table 3, that is multiples of 3. 3, 6, 9, 12, 15, 18, 21, etc. Same way multiples of 5. Multiplication table 5. 5, 10, 15, 20, 25, etc. Then next is coming multiple of 3 and 5. That means common multiple of 3 and 5. Here we can see 15 is the first common multiple. 15 is the first common multiple. So multiple of 3 and 5, the first number is coming 15. Then the next number we can find by multiplying 15 with the 2, 3, etc. If we are multiplying 15 with the 2, it will become 30. 15 into 3, 45. 15 into 4, 60, etc. So here it comes where whenever the number multiple of 3 it comes, that child supposed to say Idli, and whenever the number multiple of 5, that time the child is supposed to say Vada. And if it comes multiple of both 3 and 5, that means 15, 30, 45, etc., both the terms Idli-Vada. Now we can see children sitting in a circle. First one is saying 1. Second one 2, and third one in place of saying 3 he has to say that multiple of 3, which means he has to say Idli. For 5, in place of 5 he has to say Vada. And same way it is continuing that till the last child, one child remaining, and he is the winner of that game. So here they are saying that in the child supposed to say, the player supposed to say Idli in place of 3, 6, 9, 12, 15, 18, 12, 18, etc. And Vada in place of 5, 10, 15, 20, etc. And which is the first number for which the players should say Idli-Vada? That means 15. 15, which is a multiple of 3 and also a multiple of 5. 15 is coming in both the table, multiples of 3 and multiples of 5. And that multiples of both 3 and 5, these numbers are called common multiples of 3 and 5. So we can write common multiples of 3 and 5. 15 is the first common multiple of 3 and 5. Page number 108, figure it out. First question, at what number is Idli-Vada said for 10th time? That means the 10th occurrence of Idli-Vada. We need to find the 10th common multiple of 3 and 5. 10th common multiple of 3 and 5, that means 15. Common multiple of 3 and 5, first common multiple is 15. So 10th common multiple is of 15, that means 15 into 10, 150. So the number 150 comes, he has to say Idli-Vada, the 10th time. Second question, if the game is played for the numbers 1 to 90, find out how many times would the children say idli, including the times they say idli-vada. So 1 to 90, which means we have to take the multiples of 3, 3, 6, 9, 12, etc. up to 90. How many times multiples of 3 is coming? So it's an easy method. Just divide 90 by 3. We will get 30. That means the children would say idli 30 times. Now 2b, how many times would the children say vada, including the times they say idli-vada? So vada is set for multiples of 5. Between 1 and 90, the multiples of 5 are 5, 10, 15, 20, etc. up to 90. So how many multiples of 5 are there in between 1 and 90? That we can find 90 divided by 5, 18. So 18 multiples of 5 are there. So we can write the children would say vada 18 times. When they are playing from 1 to 90, 18 times. They are supposed to say vada in place of that number. C1. How many times would the children say idli-vada? Idli-vada is set for common multiple of 3 and 5 between 1 and 90. The first common multiple of 3 and 5, that is 15. And how many numbers or how many multiples of 15 are there in between 1 and 90? For that, 90 divided by 15 is equal to 6. So 6 multiples of 15 are there below 90 or including 90. So we can write children would say idli-vada 6 times. Third question, what if the game was played till 900? How would your answers change? So now we have learned that 1 to 90, in between 1 and 90, how many times vada the child is supposed to say, how many times idli and how many times idli-vada. Now that game is continuing till that 900. So the multiples of 3, 5 and 15 between 1 and 900 we have to calculate. Multiples of 3 up to 900, that means 900 divided by 3 is equal to 300 multiples. 300 multiples of 3 are there till 900. Multiples of 5, 900 divided by 5, 180. Multiples of 15, 900 divided by 15 is equal to 60. That means first part, the child is supposed to say idli is said 300 times. That is including the times they are saying both. Similarly, vada is said 180 times. There are also common multiple whenever it comes, that also included. Then idli-vada is said to be, that means 60 times. So the numbers will change if the game continues till that 900. Numbers are coming like the same. Fourth question, is this figure somehow related to Idli-Vada game? So we can write there, yes, this figure is related to Idli-Vada game. Here we can see these are the multiples of 3 and multiples of 5 is here. Then common multiples of 3 and 5 is coming here, common area. Included, that means both the circles part here, 15, 30, etc. Now we have to draw the figure. The game is played up till 60. So fourth question, if they are playing the game till 60, we can write multiples of 3 here in this circle and multiples of 5 in the second circle, common multiple of 3 and 5 that is coming in between. So common multiples we can see 15, 30, 45, 60. Let us now play the Idli-Vada game with different pairs of numbers 2 and 5. First one A, 2 and 5. So we have to write all the multiples of 2 in the first circle and multiples of 5 in the second circle up to 60, and the common multiples of 2 and 5 that will come over the in between here the circle, part of the both the circles included part. So 10, 20, 30, 40, 50, 60 are the common multiple of 2 and 5, and that is coming in multiple of 2 table and multiple of 5 table. Second is 3 and 7. So multiple of 3, multiples of 7, and then the common multiple of 3 and 7, that is 21 and 42. Now the third one, 4 and 6. Same way we have to draw two circles and multiples of 4 in the first circle, multiples of 6 on the second circle, and common multiples of 4 and 6 in between. Now 4 and 6, multiples of 4 here, multiples of 6, and common multiples of 4 and 6 are 12, 24, 36, 48, 60. Here yesterday we played this game with two numbers. We ended up saying just Idli or Idli-Vada, and nobody said just Vada. One of the numbers was 4. Then what was the other number? We can see here multiples of 2, that is 2, 4, 6, 8, etc. It's going. Multiples of 4, 4, 8, 12, 16, etc. So whenever the multiple of 2 that comes Idli will say, and multiples of 4, which means Idli-Vada. The common multiples of 2 and 4 is coming same as the multiple of 4. Similarly, if you are taking 8 also, multiples of 4 and 8. One is a multiple of the other one. So it will come the same way. We can write here the other number is 2. Which of the following could be the other number? That means one number is 4, the other number we can take that as 2. Next, jump jackpot. Jumpy and Grumpy play a game. Grumpy places a treasure on some number. For example, he may place it on 24. Here we can see treasure places on 24. Jumpy chooses a jump size. If he chooses 4, multiples of 4, 4, 8, 12, 16, 20, then 24. Starting at 0. Jumpy gets the treasure if he lands on the number where Grumpy placed it. So if he chooses 4, that is going 4, 8, 12, 24, 28. So it landing on 24. The other successful jumps, if he chooses the jump of 2, then also it will come on 24. 2, 4, next jump on 6, then 8, 10, like that way 24. On that number also the jump is coming. If we are taking table 3, then also it will come. 3, 6, then next jump 9, 12, 15, 18, 21, then 24. If you are taking 6 table, 6, 12, 18, then 24. If you are taking 8, first jump till 8, then from there 16, then straight from there 24. If you are taking the jump 12, straight from 0 to 12 and then 24. So any jump size 2, 3, 6, 8 and 12 can take to reach 24. So the numbers 1, 2, 3, 4, 6, 8, 12, 24 all divide 24 exactly. These numbers are called factors or divisors of 24. To find the factors or divisors of a number, we can write in this form, table format. So factors or divisors of 24. Which are the tables it coming 24 as the product. So 1 into 24, 24, 2 12s, 24, 3 8s, 24, 4 6, 24. So we have to write in order. 1 is divisible by 24, 2, 3, 4. Then 5 is not divisible by It's not going on 24 completely. Next number is 6. So after 4, 6, 7 is not going, 8, 9 it's not go, then 10, 11 not going, 12 and then 24. So we can write in order, in U shape. 1, 2, 3, 4, 6, 8, 12, 24. These are the all numbers, all divide 24 exactly. That means if you are dividing 24 by any one of these number, we will get the remainder 0. Completely we can divide. So these numbers are called factors or divisors of 24. Now Grumpy increases the level of the game. 2 treasures are kept on different numbers. Jumpy has to choose a jump size and stick to it. Jumpy gets the treasure only if he lands on both the numbers with the chosen jump size. So same as that game, here the numbers are 14 and 36. So we have to find out the factors of 14 and 36 and the common factors. Here starting with 0, he jumps to 7, 14, 21, 28, etc. It's going on. So factors of 14 are, we can see here 1, 2, 7, 14 and factors of 36, 1, 2, 3, 4, 6, 9, 12, 18 and 36. Common factors, 1 is common in both the numbers, 2 also common. No other number is common. So common factors of 14 and 36 are 1 and 2. So we can write here the jump size of 1 or 2 will land on both the numbers 14 and 36. So these numbers are called common factors. What jump size can reach both 15 and 30? There are any multiple jump sizes possible. Try to find them all. So the jump size can reach both 15 and 30. So first we have to write factors of 15. 1, 3, 5, 15. Factors of 15 we have to find by the table, using the table also. That means 1 into 15 is equal to 15. Then 2 will not go in 15. Next number is 3. 3 into 5 is equal to 15. Then 4 will not go. 5 already here reached. So the numbers we can take in U shape. 1, 3, 5 and 15. Same way we can find the factors of 30 also. First we have to write the table of 30 like the same way. Then we can see 1, 2, 3, 5, 6, 10, 15, 30 are the factors of 30. And from here common factors. 1 is common. Then 3 is common in both. 5 is common. And 15 also common. So common factors are 1, 3, 5, 15. So we can write 1, 3, 5 and 15 are the jump size. They have to choose to reach both the numbers 15 and 30. Now look at the table below. What can you notice? Here 31, 32, 33, etc. up to 70. In the table, is there anything common among the shaded numbers? The shaded numbers we can see it's a multiple of 3. 33, 36, 39, 42, 45 up to 69. So that we can write as multiple of 3. Then is there anything common among the circled numbers? 32, 36, 40, 44, 48, 56, 60, 68. Multiples of 4. Multiples of 4. All the circled numbers are multiples of 4. Then which numbers are both shaded and circled? 36, 48 and 60 are the numbers. 36, 48 and 60 are the numbers both shaded and circled. What are these numbers called? These numbers are called common multiples of 3 and 4. Common multiples of 3 and 4. Figure it out. Page number 110 and 111. First question. Find all multiples of 40 that lie between 310 and 410. Multiples of 40 that we can write easily by using the table 4. 1 times 4, 2 times 8, 3 times 12, like that way. So multiples of 40 are 40, 80, 120, 160, 200, 240, 280, 320, 360, 400, 440, etc. It's going on. Now that lie between 310 and 410. So between 310, that means after 310. So 320 is coming, 360 is there, 400 and till 410. In between 310 and 410 are the numbers 320. The multiples between 310 and 410 are 320, 360 and 440. These are the three numbers lie between, multiples of 40 lie between 310 and 410. Second question. Who am I? First one. I am a number less than 40. One of my factors is 7 and the sum of my digits is 8. So one of my factors is 7. So we have to find out the multiples of 7. Multiples of 7, that means 7, 14, 21, 28, 35. Till 35. Next multiple of 7, that is coming 42, that is above 40. Here the condition number less than 40. So we can consider the numbers till 45. Multiples of 7. 7, 14, 21, 28, 35 are the multiples of 7 which are less than 40. Now second condition. The sum of my digits is 8. Here 7 is a single digit. Sum of the digits in 14. 1 plus 4, 5. 2 plus 1, 3. 2 plus 8, 10. 3 plus 5, 8. That is the condition here. Second condition satisfying. The sum of my digits is 8. 3 plus 5 is equal to 8. So we can write that is the number is 35. So who am I? We can write. So I am 35. The number is 35. That is one of my factors, that is 7. Sum of the digits is 8 and the number less than 40. All three conditions are satisfying. So the answer is 35. Now the second part of that question. I am a number less than 100. Two of my factors are 3 and 5. Two factors are here given and the number less than 100. So we have to find the common multiple of these two factors 3 and 5. Common multiple, first common multiple of 3 and 5, that is 3 into 5, 15. So common multiples of 3 and 5, which one? First common multiple is 15 and less than 100 are 15, 30, 45, 60, 75, 90, which are less than 100. So the number will be less than 100 and also common multiple of 3 and 5. Then only these two numbers as the factors we will get. Now next condition, one of my digits is one more than the other. Now check the digits of the numbers. 15, 30, 45. Here we can see one digit is just one more than the other one. 4 plus 1, 5. So second digit is one more than the tens place digit. So we can select the number, that is 45. So one of my digits is one more than the other, that is 45. So who am I? So I am 45. Third question. A number for which the sum of all its factors is equal to twice the number is called a perfect number. Sum of all its factors is equal to twice the number. That type of numbers are called perfect number. Here 28 is a perfect number. Factors of 28, 1, 2, 4, 7, 14 and 28. When we are adding all this, their sum is coming as 56. That means 2 times of the number 28. Now find a perfect number between 1 and 10. So perfect number between 1 and 10, that is 6. Factors of 6, 1, 2, 3, 6. Then sum of factors, 1 plus 2 plus 3 plus 6, that is 12. 12 is 2 times of 6, twice of 6. So 6 is a perfect number between 1 and 10. 6 is the answer. Question number 4. Find the common factors of 20 and 28. The first one. 20 and 28. So factors of 20, 1, 2, 4, 5, 10, 20. And factors of 28, 1, 2, 4, 7, 14, 28. From that, common factors. 1 is common in both the numbers 2 and 4. So common factors are 1, 2 and 4. B. Next one, 35 and 50. Factors of 35, 1, 5, 7, 35. To find the factors, already explained here, 35 first here, try the number and write all the tables such that to get the product as 35. 1 into 35 is equal to 35. 2 is an odd number, so 2 will not go. 3 also cannot divide by 35. Then next is coming 4 will not go. Then 5. 5 into 7 is equal to 35. 6 will not go. The next number already reached here. If you are taking in order, or next number already here 7. After 7, 35 only. So we can take in order U shape. 1, 5, 7, 35 are the factors of 35. Same way we can find the factors of other numbers also. 50. So these are the factors of 50. 1, 2, 5, 10, 25, 50. Here common factors. 1 is common and 5 also in both the numbers. So common factors of 35 and 50 are 1 and 5. Next number C1, 4, 8, 12. 3 numbers are there. So factors of 4, 1, 2, 4. Factors of 8, 1, 2, 4 and 8. Factors of 12, 1, 2, 3, 4, 6 and 12. Then common factors. 1 is common, 2 and then 4. So the common factors of all these 3 numbers 4, 8 and 12 are 1, 2 and 4. Next one, 5, 15 and 25. Factors of 5, 1 and 5, 15, 1, 3, 5, 15. And factors of 25, 1, 5, 25. Common factors, all these 3 numbers. 1 is common and then 5. So common factors of 5, 15 and 25 are 1 and 5. Fifth question, find any 3 numbers that are multiples of 25 but not multiples of 50. So first we can write multiples of 25 and multiples of 50. Multiples of 25, that is 25, 50, 75, 100, 125, 150, 175, 200, etc. It's going on. Multiples of 50 means 50, 100, 150, 200, 250, 300, etc. That's going on. Now the question, any 3 numbers. The numbers that are multiples of 25 but not multiples of 50 are, from here we can see 50 is common. So before that 25 is there, 75, 25, 75, 125, etc. Common numbers no need to take. So here 100 is coming. So in between the numbers, this 150 here, both the numbers, these are the common factors. Here in this question, not the common factors. Multiples of 25 but not multiples of 50. So we can take 25, 75, 125. These are the 3 numbers. It's going on, but here in the question 3 numbers is enough. Question number 6. Anshu and his friends play the Idli-Vada game with 2 numbers which are both smaller than 10. The first time anybody says Idli-Vada is after the number 50. So the first time they are saying Idli-Vada, both the term together, that the after the number 50. which means first time Idli-Vada is at after the number 50. That means the first common multiple of these two numbers, that must be slightly greater than 50. The first common multiple of the numbers must be slightly greater than 50. So we can check the numbers. If you are taking 7 sevens are 49, that is less than 50. So till 7 all the numbers when we are taking, that is less than 50. Now it's after 50. So if we are taking 7 and 8 as the number, 7 into 8 we can write 56. If we are taking 7 and 9, that also below 10, the number is supposed to be below 10. 7 and 9, that is here given, they are smaller than 10. So if we are taking 7 and 9, 7 into 9, that will come 63. Also we can think about 8 and 9. If 8 and 9, then 8 into 9, that is coming 72. Out of this we can see 56 is the smaller number, just after 50, and 7 and 8, both the numbers are less than 10. So we can write the numbers. We have to find what could the two numbers be which are assigned for Idli and Vada. So we can write, that is the two numbers could be 7 and 8. 7 and 8. So this can also can come. That means the first common multiple is coming greater than or above 50. But just soon after 50 we are getting, if we are taking 7 and 8 the numbers. So the two numbers are 7 and 8. Multiples of 7, wherever it comes, that he has to say Idli, and multiples of 8, it comes Vada. He has to say Vada, and the common multiple, first common multiple is 56. That time, first time, the child is supposed to say Idli-Vada. Question number 7. In the treasure hunting game, Grumpy has kept treasures on 28 and 70. What jump sizes will land on both the numbers 28 and 70. So first we have to write factors of 28, factors of 70, and common factors. Here 1, 2, 7 and 14 are the common factors of 28 and 70. So these are the jump sizes. So you can write in sentence, the jump sizes which will land on both the numbers 28 and 70 are 1, 2, 7 and 14. Question number 8. In the given diagram below, Guna has erased all the numbers except the common multiples. Find out that those numbers could be filled in the missing numbers in the empty regions. So here we can see the common multiple. The smallest common multiple is 24. Common multiples are 24, 48, 72, and the least one is 24. That means the first common multiple of two numbers, that is 24. So first we have to find the factors of 24. We can see 1, 2, 3, 4, 6, 8, 12, 24 are the factors. And multiples of two numbers when we are taking, 1 we no need to take. So we can cut out that one. Then here 3 pairs are there. 2 and 12, 3 and 8, 4 and 6. Here we can see if we are taking 2 and 12, 12 is the first common multiple. 12 is supposed to come first common multiple if the numbers are 2 and 12. But 12 is not here. So this one is not possible. Then 4 and 6. That also 12 is supposed to come as the first common multiple. When we are taking in table 4, 12 is coming. In table 6 also 12 is coming. So 12 is not a common multiple of not a common multiple in the given figure. So that number also, that pair also not possible. Then the remaining is 3 and 8. If we are taking the numbers 3 and 8, first common multiple of 3 and 8, that will come as 24, and that is here given. So we can write the numbers, multiples of the first column that contains 3 and the second column multiples of 8. Then we can fill the numbers here. So multiples of 3 we can write in the first region, empty region, 3, 6, 9, 12, 15, 18, 21, 27, etc. And here multiples of 8, 8, 16, 32, 40, 56, rest of the numbers here, 24 and 48. 40, then 48, 56, 64, etc. Here the highest common multiple is given 72. Question number 9. Find the smallest number that is a multiple of all the numbers from 1 to 10 except 7. And the 10th question also is connected. Find the smallest number that is a multiple of all the numbers from 1 to 10. From 1 to 10 all the numbers, and find the smallest number that is a multiple of all these numbers. Here except 7. So first we have to find the smallest multiple, the least multiple of all these numbers. That means same as the LCM of these numbers. Here the 9th question, the smallest number that is a multiple of all the numbers from 1 to 10 except for 7. The smallest number or a multiple, that means the LCM, least common multiple, first common multiple. For that we have tried the numbers 1 to 10 here. 1 and its factors. 2, solve one time, 3 one time, 4 prime numbers. 4 we know that 2 into 2, 5 is 1 time, 6 is 2 into 3, 8 is 2 cube, 3 times 2. 9 is 3 square, 10 is 2 into 5. And LCM means the product of the highest power of the prime numbers or prime factors. Here 1 no need to take. 2, that the highest power is coming here, 2 cube. Here 2 square is there, we have to take the highest one, 2 cube, which means 2 cube means 3 2's. Then the highest power of 3, that is coming 3 square. Here 2 times 3, 3 square. Then next number is 5 only here. 2 already we have taken. 1, 2, 3, this all we here, 2, 3, 5, next one is coming 5, 5 here the power is 1, here also power is 1. So 1 time we are taking here. When we are multiplying, what we are getting, the product of these numbers 2 into 2 into 2 into 3 into 3 into 5 is equal to 360. So the smallest number that is a multiple of all the numbers from 1 to 10 except 7 is equal to 360. Now the 10th question including that 7 also. Same way we have to do, and we have to take that 7 also. When we are taking 7, that means here supposed to come that 7. Here 7 factors, that just 1 into 7, that means 7 itself. So we have to multiply this number with 7. Already we got here 360. That 3 times 2, 2 times 3 and 1 5. Till here it was here, and now we are multiplying that answer with 7. We will get 2520. So the smallest number that is a multiple of all the numbers from 1 to 10 is 2520. This is the 10th one answer. Here without that 7, that means 360. LCM of all these numbers from 1 to 10. Prime numbers. Guna and Anshu want to pick figs that grow in their farm. Guna wants to put 12 figs in each box. Anshu wants to put 7 figs in each box. So think different ways how they are arranging. Guna can arrange 12 figs in rectangular manner. Here we can see Guna what she is doing, 12 in rectangular manner, 12 into 1. Here 6 rows each with 2. So 6 into 2, that also we will get as 12. Here 4 rows and 3 columns. That way also she can arrange. 4 into 3, 12, 6 into 2, 12, 12 into 1, that also 12. But Anshu can arrange 7 figs in rectangular manner, which means only horizontally here. Horizontally or vertically. 1 into 7 or 7 into 1. In that method only. No other rectangular method she cannot apply. So here Anshu could make only one arrangement. 7 into 1 or 1 into 7. So Guna's arrangement 12 we can arrange in different way. So here they are saying, we saw that the number 12 can be arranged in a rectangle in more than one way. That means 12 has more than 2 factors. The number 7 can be arranged in only one way. It has only 2 factors. Which are the factors? 1 and 7. 1 and 7 are the factors of 7. But 12 is having more than 2 factors. 12 and 1, 6 and 2, 4 and 3 are the factors of 12. So, if the numbers having only 2 factors, numbers that have only 2 factors are called prime numbers or primes. Examples for that, the number 2, 3, 5, 7, 11, 13, 17, 19, etc. These are prime numbers which is having only 2 factors. 3 we can write only 1 into 3. 2 as 1 into 2. 17, 1 into 17, no other factors. 1 and the number itself are the factors of prime numbers. At the same time, composite numbers which have more than 2 factors. If a number is having more than 2 factors, that is called composite numbers. The first few composite numbers are 4, 6, 8, 9, etc. Now about the number 1. The number 1 is neither a prime nor a composite number. 1 is not in prime numbers list and not in composite numbers list. Now in summary we can say that prime numbers means the numbers that have only 2 factors are called prime numbers or primes. Example 2 we can write only one method 1 into 2. 3 we can write as 1 into 3, 5 as 1 into 5, 7 or factors of 7, 1 and 7. That means the number itself and 1 and the number itself. Such type of numbers are called prime numbers. Here the examples, first few prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, etc. It's going on. So each prime number we can see that can write as 1 into that number. Product of 1 and the number itself. Now the composite number. A number that has more than 2 different factors. Then we can say as a composite number. For example 4. 4 we can write as 1 into 4. 4 we can write as 1 into 4 and 2 into 2. So the factors are coming 1, 2 and 4. More than 2 factors are there. Same way 6. 1 into 6 and 2 into 3. 4 factors are there. 1, 2, 3, 6 are the factors of 6. So these type of numbers if they is having more than 2 factors, then we can say that as composite numbers. Examples 4, 6, 8, 9, 10, 12, 14, 15, etc. are the composite numbers. Now the number 1. 1 is not in any one of these group. Now 1 is neither a prime nor a composite number. Because 1 is having only one factor. 1 we can write as 1 into 1. Which means only 1 as the factor. Prime numbers having 2 factors, 1 and the number itself. 7, 1 and the number, 2 factors. If the number is having 2 factors, that is called prime. More than 2 factors, that is called composite number. And 1 is not included in prime or composite numbers list. Now how to find out prime numbers and composite numbers in the table from 1 to 100. First we have to cross out 1 is not in prime or composite, neither prime nor a composite. So first just cut that number 1. Then circle 2. 2 is a prime number. And all the multiples of 2 we have to cross out. 4, 6, 8, 10, 12, 14, 16, etc. up to 100. All even numbers first you have to cross out. Then take the next number 3. 3 is the next prime number. Circle that number and then cross out all the multiples of 3. After that 5. 5 also next prime number. Then circle the number 5. Rest of that all multiples of 5 that you have to cross out. Continue the same way. 7, 11, 13, etc. Then we will get all the circled numbers are prime numbers and all the crossed numbers are composite numbers except 1. Now here, how many prime numbers are there from 21 to 30? Look at the table here. From 21 to 30, the circled numbers 23 and 29. So we can write the answer from 21 to 30, 23 and 29, two prime numbers are there. 23 is having the factors 1 and 23, 29 is having 1 and 29. Now how many composite numbers are there from 21 to 30? Rest of the numbers 21, 22, 24, 25, 26, 27, 28 and 30 are the composite numbers from 21 to 30. Here we can see all the circled numbers are prime numbers and all the crossed out numbers other than 1 except 1 are composite numbers. This method is called sieve of Eratosthenes. Sieve of Eratosthenes, that means you have to write the numbers from 1 to 100 and cross out the first number 1 that is not in the primes or composite numbers list, and then circle the prime numbers, cross out the multiples of that prime numbers. Figure it out. First question, we see that 2 is a prime and also an even number. Is there any other even prime? No, there is no other even prime. Only 2 is the only even prime number. Second question, look at the list of primes till 100. What is the smallest difference between two successive primes and what is the largest difference? So we have to look at the previous page, that table 1 to 100 all the primes. Here we can see the smallest difference. These two are the nearest primes, 2 and 3. The smallest difference between that is 1. 3 minus 2 is 1. And the largest difference, that means everywhere we can see 2 or more than primes, every row. Now in the last row only one prime number. So the difference between 89 and 97, that means 1, 2, 3, 4, 5, 6, 7, 8. Difference is 897 and 89. So we can write this the largest difference. So we can write the answer here. Difference between the first two prime numbers 2 and 3, that is 1. 3 minus 2 is 1. So the smallest difference here, two parts are there. Find the smallest difference between two successive primes. So the answer is up to 100, that is 1. The smallest difference between two successive primes up to 100, that is 1. And the largest difference between two successive primes up to 100 is 8. That is coming in between the primes 89 and 97. Third question, there are equal number of primes occurring every row in the table of the previous page. Which decade have the least number of primes and which have the most number of primes? Now here already we noticed that the decade 91 to 99, this one is having only one prime and the first two row is having 4 primes. Here for this row is also having 4 primes. So we can write in sentence. Here the question, are there an equal number of primes occurring every row? No, there is not an equal number of primes in every row. Then the second part, which decade have the least number of primes and which have the most number of primes? So the decade 90 to 99, last row, has the least number of primes. There is only one prime number 97 in the last row. the decades 0 to 9 and 10 to 19. That means the first two rows have the greatest number of primes. Each row is having 4 primes. Question number 4. Which of the following numbers are prime? Here 23, 51, 37, 26. We can see here 23 we can write as 1 into 23. That means the factors are 1 and 23. 51 we can write as 1 into 51. That is equal to 51. 3 into 17 also is equal to 51. So the factors are coming 1, 3, 17 and 51. More than 2 factors are there. Here 37 is having only 2 factors, 1 and 37. 26 is having 1, 2, 13, 26. More than 2 factors. So these two numbers is having more than 2 factors. That means composite numbers. Here the question, which are the numbers are prime. So we can see 1 and the number itself. Only 2 factors. These two numbers are the prime numbers. 23 and 37 are prime numbers from these out of these given numbers. Fifth question, write 3 pairs of prime numbers less than 20 whose sum is a multiple of 5. We will get many prime numbers less than 20 whose sum is a multiple of 5. If you are taking 2 and 3, you have to take only prime numbers and sum is a multiple of 5. 2 plus 3, 5, that is a multiple of 5. 5 into 1, 5. 2 and 13, 15. 7 plus 13, 20. 11 plus 19, 30. 13 plus 17, 30. Here 3 plus 7, 10. 3 plus 17, 20. So all these pairs is having sum is a multiple of 5. So we can take any 3. Question number 6. The numbers 13, 31 are prime numbers. Both these numbers have the same digit 1 and 3. Find such pairs of numbers up to 100. So we can write, if we are looking the prime numbers list, prime numbers consist of the same digits are 13, 31, 17, 71, 37, 73, 3 and 7, 7, 9, 9, 7, 79 and 97. These are with the same digits. Now next question, 7th one. Find 7 consecutive composite numbers between 1 and 100. We can see that in the last decade, the last row, the 7 consecutive composite numbers 90, 91, 92, 93, 94, 95, 96. Next number 97 is prime. Rest of all these numbers are composite numbers. So 7 consecutive means continuous composite numbers are from 9 to 96. 8th question. Twin primes are pairs of primes having difference of 2. So twin prime numbers, which means it's a pair of prime numbers having difference of 2. Example 3 and 5. The difference between these two numbers, that is 2. 17 and 19. Now find the other twin primes between 1 and 100. Here 3 and 5 already it's given. 17 and 19 also it's given. But when we are writing twin primes between 1 and 100 are including that, all this. Except these two means rest of that. So here we can see the difference between the prime numbers in this pair. That is 2 everywhere. 71 and 73, 2. 59 and 61, that is 2. 41, 43, 2. If the difference between two prime numbers is 2, then we can say that is twin primes. Now 9a, 2 is a prime and so is the next number 3. For every other prime, the next number is composite. That statement is true. For every prime number other than 2, the next number is composite. Only for 2, after 2, 2, then 3 is coming. 2 continuous numbers are prime. So we can write the statement is true. For every prime number other than 2, the next number is composite. Question number 10. Which of the following numbers is the product of exactly 3 distinct numbers? 45, 60, 91, 105, 330. So we can write the prime factors of these numbers or prime factorization of these numbers. 45, when we are doing the prime factorization, we will get 3 into 3 into 5. That means 3 and 5, two distinct primes. Distinct means different primes. 60 we are getting 2 times 3 and 5. So here 3 distinct primes are there, but 2 is repeating. Here 91, 7 and 13, that means 2 distinct primes. 105, 3 into 5 into 7, which means 3 distinct prime numbers. 330, here 4 distinct prime numbers. Here the question is exactly 3 distinct prime numbers. So we can say 105, 3, 5, 7, 3 different prime numbers are there. So 105 is the product of exactly 3 distinct prime numbers. That is 3 into 5 into 7. 3, 5, 7 are the prime numbers and its product is equal to 105. 11th question. How many 3-digit prime numbers can you make using each of 2, 4 and 5 ones? There is no such number. So we can write none. A 3-digit number ending with 2 or 4 is divisible by 2, and a 3-digit number ending with 5, that will be divisible by 5. So using these 3 digits, if any 3-digit number ending with 2 or 4, that is an even number, which means that is divisible by 2. If a 3-digit number ending with 5, anyway that number is divisible by 5. So there is no prime number, 3-digit prime number using these 3 digits. 12th question. Observe that 3 is a prime number and 2 into 3 plus 1 is equal to 7 is also a prime. Are there other primes for which doubling and adding 1 gives another prime? Yes. Find at least 5 such examples. So we can write 2, 3, 5, 11 and 23 are the 5 numbers, such type of the numbers. That means 2 we can write as 2 into 2 plus 1 is equal to 5. 5 is a prime number. 2 into 3, 6 plus 1, 7. 2 into 5, 10 plus 1, 11. 2 into 11, 22 plus 1, 23. 2 into 23, 46 plus 1, 47. So we are getting all these numbers as prime. We can write these are 5 prime numbers for which doubling and adding. Doubling means multiplying the number by 2. And adding 1 gives another prime. Co-prime numbers. Here which pairs are safe? Let us go back to the treasure finding game. In this time treasures are kept on 2 numbers. Empty gets the treasure only if he is able to reach both the numbers with the same jump size. And here is the new rule. A jump size of 1 is not allowed. So both the numbers have no common factor, then we can say that numbers are co-prime numbers. If they are keeping such type of numbers, then we can say the pairs are safe. Here the example, some numbers are given. We have to check that. Check if these pairs are safe or not. Now the definition of co-prime numbers, that is 2 numbers are said to be co-prime if they have no common factor other than 1. Here we are going to check the numbers 15 and 39. 15 we can write that as 3 into 5. 39 we can write that as 3 into 13. Here we can see 3 is a common factor in both the numbers. So we can say that number is not safe. Next 4. 4 when we are doing the prime factorization, we can write that as 2 into 2. 15 we can write as 3 into 5. Here is no common factor. So these numbers are safe. Next one 18 and 29. 18 we can write as 2 into 3 into 3 in terms of prime numbers. 29 already it's a prime number. So there are also no common factor, which means these numbers are safe to keep the treasure. Next 20 and 55. 20 we can write as 2 into 5 and 55 5 into 11. Here 5 is a common factor in both the numbers. So if they are choosing the jump size 5, he can reach both the numbers. So that number, these two numbers are not safe. So only 4 and 15 or 18 and 29 are safe to keep the treasure there and in this game. So these type of numbers, if there is no common factor, then we can say such type of numbers are co-prime. Here the definition is given. Two numbers are said to be co-prime to each other if they have no common factor other than 1. Such type of numbers are called co-prime numbers. Now here the question is given. Which of the following pairs of numbers are co-prime? First one 18 and 35. Page number 116. First one 18 and 35. Here 18 we know that we can write that as 2 into 9, which means 2 into 3 into 3, and 35 we can write as 5 into 7. Here no common factor. So we can write these are co-prime numbers. Same way when we are checking the rest of the numbers, we can see that 15 and 37. 15 we can split as 3 into 5. 37 is a prime number. There is no common number or common factor. So we can write these two numbers are co-prime numbers. Next 30 and 415. 30 we can do the prime factorization. After that we will get 2 into 3 into 5. 415 is coming 5 into 83. Here 5 is coming in both the numbers. That means we can divide by 5 both the numbers. Or if they are choosing the gem size 5, they can reach both the numbers. So we can write here 5 is a common factor in both the numbers. Therefore, that is not, these two numbers are not co-prime. Next 17 and 69. 17 itself is a prime number. 69 we can write as 3 into 23. So these two numbers have no common factor. Therefore, we can write 17 and 69 are co-prime numbers. 81 and 18. When we are splitting, we will get here 3 into 3 into 3 into 3 as 81. 18 as 2 into 3 into 3. Here we can see 3 we can take as a common factor. Also 3 into 3. 9 is a common factor. So there is any common factor, then we can write these two numbers are not co-prime. So the co-prime numbers are 18 and 35, 15 and 37 and 17 and 69 out of this. Here sometimes the first common multiple was the same as the product of two numbers. At other times the first common multiple was less than the product of two numbers. Find examples for each of the above. So sometimes the first common multiple was the same as the product of two numbers. When if the numbers is having no common factor, then the product of two numbers same as the first common multiple. For example, 4 and 5 we are taking, we can see here is no common multiple. Here no common multiple or common factor. If there is no common factor, not multiple, common factor, then we can see the first common multiple. First common multiple is coming that as 20. 4 into 5. At the same time, the second case, what is coming? Sometimes the product of the less than the product of two numbers. If we are taking, for example, 4 and 6, we know that there is 2 is a common factor. Here, 2 is a common factor. So the first common factor, the first common multiple of these two numbers is coming as 12, which is less than the product. Product of these two numbers 4 into 6, 24, and the first common multiple is coming less than the product if there is any common factor. In the first case, if there is no common factor in the given numbers, then the first common multiple will be equal to the product of two numbers. At the same time, if any common factor for the given numbers, then the first common multiple that will be less than the product of two numbers. Next is prime factorization. Prime factorization of a number, which means we have to write the number as the product of all the prime numbers. Here 56 we can write different way, 4 into 14 or 4 into 2 into 7. Again here we can see the composite numbers are coming. So by splitting again and again the composite number, till getting all the numbers as prime, we have to split that and get the prime factorization. So 4 we can write as 2 into 2, 14 we can write as 2 into 7. The easiest method or the simplest method to find the prime factorization of a number is to keep on dividing the number by prime numbers until the remainder is equal to 1 or until the remainder gets 1. In this case, the number is 36. 36 we can write different way or using different tables. 2 into 18 is 36, 3 into 12 is 36, 4 into 9 36, 6 into 6 36. So whatever we are taking, we have to keep on splitting the term. Composite number, we have to split it. Here 2 is the prime number, write the same as that. 18 we have to split as 2 into 9, then that 9 as 3 into 3. Here 12 is the composite number, that we can write as 3 into 4. Again 4 is a composite number, that is 2 into 2. Here 4 is a composite number, 2 into 2. 9 we can write as 3 into 3. Same way here 6 we can write 2 into 3. The other 6 also the same way. After, if we are looking, we can see the final answer in all these methods getting the same. 2 times 2 and 2 times 3. Everywhere we can see that. So here the final answer is containing only prime numbers. For the prime factorization, there is two different methods. One is splitting, keep on dividing the composite number or splitting the composite number till getting the all numbers as prime. 225, 3 into 3 into 5 into 5. 30, we know that 6 5s are, so 6 we can split as 2 into 3 and into 5. Here 72 we can write as 12 into 6. But that 12 again we can write as 2 into 2 into 3. 6 we can write as 2 into 3. Then all together 72 is coming as in place of 12, 2 times 2 and 3. Here in place of 6, 1, 2 and 3. When we are writing here, this is for 12 and this for 6, and rearrange that 3 times 2 and 2 times 3. And another method, the division method, prime factorization till getting 1 as the remainder. So now we can see this is the definition of prime factorization. A number as a product of only prime numbers, then it's called prime factorization. The simplest method to find the prime factorization is the dividing the number by prime factors until the remainder equal to 1. For example, 30 here, that we can divide. 30 is an even number. First prime number is 2. Divide by 2. Then we will get that as 15. Again divide by 3, 5 and divide by 5, 1. So 30 we can write in terms of prime numbers product 2 into 3 into 5. 72 when we are doing here, it's an even number. Divide by 2, we'll get 36. Again divide by 2, 18. Divide by 2, 9. And then after that is an odd number. Check the 3 table. First prime number is 2, then next prime number. If not possible division by 2, then take the next prime number, that is 3. So 9 divided by 3, 3 and one more time 3, 1. So we can write 72 is equal to 2 into 2 into 2 into 3 into 3. Now figure it out. Page number 120. First question. Find the prime factorization of the following numbers. First is 64. So 64 we can do by splitting that 8 into 8 and 8 again we can split as 2 into 4. This 8 also we can split as 2 into 4. And again 4 is a composite number. So we can write already these 2 same as that. 4 we can write as 2 into 2. This 2 same as that. Here also this 2 same as that. 4 again we can write that as 2 into 2. Now we are getting 6 times 2. So we can write 64 is equal to 2 into 2 into 2, again 2 into 2 into 2. That means 6 times. If we are doing the division method, 64 divided by 2, we will get that as 32. Again divide by 2, that will come 16, and divide by 2. Divide by 2, it will come 8. Again divide by 2, 4. Divide by 2, 2. Divide by 2, 1. Till getting 1. That means here 3 2's, again 3 2's, total 6 2's. Both the method same way we will get the answer. Now the next number is 104. 104, when we are splitting that, we can write as 8 into 13, and this 8 we can split as 2 into 4, and that into 13 same as that. Again 4 is a composite number, this 2 same as that. 4 we can split as 2 into 2, and here 13 same as that. So we are getting the prime factorization of 104 as 3 times 2 and 30. Same thing here, if you are divide by 2, it will come 5 times 2 in 10 and 2 times. Again divide by 2, 2 times in 5, 4, and remainder is 1. So 12, there 6 times, 1 more 2, here 1 time, and here 3. 13 is a prime number, so 13 itself 1. 3 times 2 and 30. Both the methods, we can any one of that method we can apply. This is the by splitting the terms, composite numbers, and this is the division method. Next number is 105. Here we are getting 3 into 5 into 7. 243. When we are dividing by 3, 81, again by 3, 27, 9, 3. So we are getting 5 times 3, 320. Here we are getting 6 times 2 and 1, 5. 141, directly 3 into 47. 1728. Here we are getting 6 times 2 and 3 times 3. So these are the prime factorization of the numbers. That means the given number we can write as the product of prime numbers. Next number 729. There we are getting 6 times 3. 1024. Here 10 times 2. 1331, 3 times 11. 1000, 3 times 2 and 3 times 5. It's the prime factorization of all the given numbers. Second question, the prime factorization of a number has 1, 2, 2 3's and 1 11. What is the number? So you have to multiply all the prime numbers. So we can write the required number is 1, 2, 2 times 3 and 1, 11. When we are multiplying this, we will get 198. So 198 is the number. Now third question, find 3 prime numbers all less than 30 whose product is 1955. So to find the prime numbers of this product, we have to factorize that, prime factorize that. When we are doing the prime factorization, this is an odd number, so we cannot divide by 2. We know that the first prime number is 2. So check the number by 2. It's an odd number, so we cannot divide by 2. Next we check with 3, and after that next one 5. So here we are taking 5, dividing. This number is divisible by 5. So when we will get 391, after that by 70, then by 23. So here we can see the prime numbers 5, 17 and 23 are less than 30 and whose product is 1955. So these are the numbers. Fourth question, find the prime factorization of these numbers without multiplying. First here 56 into 2, 25, product of two numbers. So we have to write the prime factorization of both the numbers. 56 we can write as 56 when we are dividing by 2, it will come here in 5 2 times 16, there it will come 8, again by 2 14, again by 2 7 and divide by 7 it will come 1. That means 3, 2 and 7. 25 we know that 5 into 5. Then prime factorization of 56 into 25, it will come 3 times 2 and 2 times 5 then 7. Same way the next numbers 108 into 75. 108 we can split as 2 into 2 into 3 into 3 into 3. 75 was 3 into 5 into 5. Then prime factorization of this both the numbers. So 108 into 75 is here 2 times 2 and 3 plus 1. 4 times 3, 2 times 5. Next number 1000 into 81. 1000 we can write as 3 2's and 3 5's. 81 as 4 3's. Then prime factorization of the product 1000 into 81 is here 3 2, 4 3 and 3 5's. Question number 5. What is the smallest number whose prime factorization has 3 different prime numbers? 3 different prime numbers. The smallest number we have to find. So we have to multiply the smallest prime numbers. First prime number, that is 2, then 3, then 5. So we can write the smallest 3 different prime numbers, which means 2, 3 and 5. So the smallest number whose prime factorization has 3 different prime numbers is 2 into 3 into 5, that means 30. Second part, 4 different prime numbers. So we have to take the smallest 4 prime numbers, the first 4 prime numbers, 2, 3, 5 and 7. Then the smallest number whose prime factorization has 4 different prime numbers, which means 2 into 3 into 5 into 7 is equal to 210. Figure it out. Page number 122. First question, are the following pairs of numbers co-prime? Because first and then use prime factorization to verify your answer. First one 30 and 45. So first we have to find the factors of 30 and 45. Factors of 30, factors of 45 and look at that common factors. Here 1 is common, 3 is there in both the numbers and 5 is there in both the numbers, also 15 is there. So common factors are 1, 3, 5 and 15. If there are any common factor, we can say that is not co-prime. So 30 and 45 is not a pair of co-prime numbers. Next is 57 and 85. 57 we can write as 3 into 19. 85 we can write as 5 into 17. So there is no common factor. Here no common factor other than 1. Any number we can write as 1, but co-prime numbers means if there is no common factor other than 1, then we can say the numbers are co-prime. That means 57 and 85 are co-prime numbers. Next number 121 and 1331. 121 we can write as 11 into 11. 1331 as 11 into 11 into 11. Here common factors, 2 set of 11 is there. Common factor. So we can take that as 121. 121 is a common factor in both. So we can write these two numbers are not a pair of co-prime numbers. Next one 343 and 216. 343 as 7 into 7 into 7. 216 as 3 times 2 and 3 times 3. Here no common factor other than 1. Therefore these two numbers are co-prime numbers. Second question, is the first number is divisible by the second? Use prime factorization. The first one, 225 and 27. Here 225, when we are doing the prime factorization, 3 into 3 into 5 into 5. 27 is 3 into 3 into 3. And the first number is divisible by the second or not. If the first number is divisible by the second, then that all the factors of the second number supposed to be there in the first one. Here 225 does not have enough factors of 3. Here only 2, 3. But 27 contains 3 times 3. So which means first number is not having enough number of 3 in this case. So we can write 225 is not divisible by 27. Second number, 96 and 24. 96 we can write and 24 as 3 2s and 1 3. Here 4 5 2s and 3. Here we can see these 3 2s already there and 1 3 here in 24, that also there in 96. Which means 96 includes all the factors of 24, the second number. Therefore, 96 is divisible by 24. Next one, 343 and 17. 343 is 7 into 7 into 7. 17 is 1 into 17. And 343 is not have the 17 factor. Which means 343 is not divisible by 17. Next one, 999 and 99. Here 3 3s and 137. Here 2 3s and 111. Which means the first number is not included all the factors. 11 is not there. 3 is there. 2 3s are here and here. That is not enough. The other factor 11 also supposed to come over here. So 999 does not include all the factors of 99. Does not include 11 here. Therefore, the first number is not divisible by the second number 99. Third question, the first number has prime factorization 2 into 3 into 7 and the second number has prime factorization 3 into 7 into 11. Are they a co-prime? Does one of them divide the other? Here co-prime means we can see 3 into 7, 3 into 7 are common factors. So we can write these two numbers are not co-prime. And are they are divisible? They are not divisible because the first number is not containing the second, all the factors of second term. So we can write both the numbers having common factors 3 and 7. So they are not co-prime. Then does one of them divide the other? For that we can write no. So we can write that these numbers not included all the factors of the other. So not divisible. Here 11 is there, that 11 is not here. The same way here 2, that is not coming in the second number's prime factorization. So these are not divisible. Fourth question, Guna says any two prime numbers are co-prime. Is he right? Yes, what he is saying is right. Guna is right. We know that any two prime numbers are co-prime as they do not have any common factor other than 1, which means they are always co-prime numbers. Now for example, the prime numbers are 2, 3, 5, 7, 11, 13, etc. If you are taking any two primes, we can see there is no common factor for that. So we can write they are always co-prime. Any two prime numbers from the prime numbers list, there is no common factor other than 1, which means all these numbers are co-prime. Divisibility test. A big numbers we can check by through simple methods are divisible by these numbers or not. First, a number is divisible by 2 or not. For that, look at the given number and its units digits ending with or units digits is 0, 2, 4, 6 or 8, which means the number is an even number, then that number is divisible by 2. Divisibility test of 3. Sum of all the digits in a is a multiple of 3. Sum of all the digits. First you have to add all the digits of the given number, and that is a multiple of 3. Then we can say the given number is divisible by 3. Divisibility test of 4. The last 2 digits of the given number. If the last 2 digits, that means 1s and 10s digit, it's divisible by 4, then that given number, big number, also divisible by 4. 5. The number ends with 0 or 5, then the given number will be divisible by 5. For 6, the number is divisible by 2 and 3. That's supposed to be an even number and also divisible by 3. 3, that we have to check by using this method. First you have to add all the digits, and that is a multiple of 3. Then we can say that number is divisible by 3. If it is an even number, then we can say that is divisible by 2. If both 2 and 3 divisible by 2 and 3, then we can say the given number is divisible by 6. For 8, last 3 digits divisible by 8. Then the given number, that will be divisible by 8. 9, sum of all the digits is a multiple of 9. Same as that 3. If all the first you have to add all the digits, and that sum is a multiple of 9, then we can say the given number is divisible by 9. 10, if the number ends in 0, that means unit place digit is 0, then we can say that number is divisible by 10. Figure it out. Page number 125. First question, 2024 is a leap year, as February has 29 days. Leap year means February is having 29 days. Leap years occur in the years that are multiples of 4, except for those years that are evenly divisible by 100 but not 400. From the year you were born till now, which years were leap years? We can take that 2010 or 9 if you want. Then after that the next leap year is 2012, then plus 4 with that. 2016, 2020, then 2024. Second part, from the year 2024 till 2099, how many leap years are there? So we can write in order. Just keep on adding 4. 2024 is a leap year. Then 28, 32, 36, 40, 44, 48, 52, 56, 60, 64, 68, 72, 76, 80, 84, 88, 92 and 2096. So there are altogether 19 leap years from 2024 till 2099. Second question, find the largest and smallest 4-digit numbers that are divisible by 4 and also palindromes. Palindromes means when we are writing forward and backward, the same order keeping numbers. Now the largest 4-digit number which is divisible by 4 and also palindrome, which means 8,888. And the smallest number also, smallest 4-digit number divisible by 4 and is also palindrome, that is coming 2112. Here we can see the numbers when we are writing in forward 2, 1, 1, 2. If we are starting from here also, we will get the same number 2, 1, 1, 2. So these type of numbers are called palindrome. Now the third question, explore and find out if each statement is always true or sometimes true or never true. You can give examples to support your reason. First one, sum of two even numbers gives a multiple of 4. So we can write that not always, sometimes true. So not always, or we can write that as sometimes. Sometimes true. Example, 6 plus 4 is equal to 10, which is not divisible by 4. Adding two even numbers, not always a multiple of 4, which is not divisible by 4. Here 2 plus 6, 8, which is divisible by 4. Second one, sum of two odd numbers gives a multiple of 4. Here odd numbers 7 and 3, if we are adding 10, which is not a multiple of 4, 7 plus 5 is equal to 12 that is a multiple of 4. So there also sometimes these statements it will become true. Here divisible or multiple we can write it. Question number 4. Find the remainders obtained when each of the following numbers divisible by 10, 5 and 2. We can take the first number 78. 78 when we are dividing by 10, we know that 7 is the quotient and 8 will be the remainder. So remainder only we have to write here. Remainder is equal to 8. 78 divided by 5. So it will come 8 minus 5, 3. 3 is the remainder. 78 is an even number. So when we are dividing by 2, remainder will be 0. Next number 99. 99 divided by 10, remainder will become 9 because 9 times 10 in 90 and then 9 is the remainder. Dividing by 5, 9 minus 5, that means 4 is the remainder. 99 is an odd number, so dividing by 2, 1 will be the remainder. Now same way the rest of the numbers. Next one, 173 divided by 10. Here we can see 3 is the remainder. Dividing by 5, there also 3 is the remainder. Dividing by 2, 1 is the remainder. 572, here 2 is the remainder. Here also dividing by 5, there also 2 is the remainder. It's an even number, so 0 is the remainder. Next number 980. In ones place 0, that means which is divisible by 10, remainder is 0. Divisible by 5, remainder is 0. Divisible by 2, remainder is 0. Next number 1111, dividing by 10, 1 is the remainder. Dividing by 5 also 1 and by 2 also 1 is the remainder. Next number 2345, dividing by 10, 5 is the remainder. By 5, this number is divisible by 5, so 0. So an odd number, therefore remainder, when we are dividing by 2, remainder will come 1. Fifth question, the teacher asked if 14,560 is divisible by all these 4, 2, 4, 5 and 8 and 10. Guna checked for divisibility of 14,560 by only 2 of these numbers and declared that it was also divisible by all other numbers. What could those 2 numbers be? We know that 2, 4, 8. These are the multiples. If he checked with 8, then automatically that number will be divisible by 2 and 4 also. If he checked by 10, then that number will be divisible by 5 also. So the numbers he checked may be that 8 and 10. So we can write, if a number is divisible by 8, it is also divisible by 2 and 4 because 8 is a multiple of 2 and 4. If a number is divisible by 10, then also we can write it is also divisible by 5. Therefore, Purna could check the number 14,560 by 8 and 10. Question number 6. Which of the following numbers are divisible by 2, 4, 5, 8 and 10? We can see these 2 numbers are not divisible by 10 because unit place digit is not 0. So these 2 cannot divide by 10. Here all these numbers can divide by 10 and also by 8. 8 is a multiple of 56 is a multiple of 8. Here 3 zeros are coming, that means that also we can divide by 8 and this. So the answer is these 3 numbers are divisible by all the given terms. Question number 7. Write 2 numbers whose product is 10,000. The 2 numbers should not have 0 as the units digit. So first we have to split the 10,000 as 10 into 10, 10 into 10. And again this 10 as 2 into 5. 2 into 5, 2 into 5 and 2 into 5. We can write all 2's together. 2, 2, 2, 4 2's are here and 4 5's are there. So when we are multiplying these 4 2's, we will get 16 and 4 5's 625. So the numbers are 16 and 625 are the 2 numbers whose product is 10,000 and not ending with 0. Here page number 127, puzzles, first column. Here we can see 105 as the product of these three numbers. At the same time, product of these three vertically, that is equal to 28. So prime factorize these two numbers and we can rearrange it getting such that product horizontally that is 105 and vertically that is 28. So if we are writing the numbers, for example 105, when we are prime factorizing, we will get the factors 3, 5, 7. So we have to put in correct way such that the vertical column supposed to get as the product 28. So 7, 5, 3 are the factors. Same way 20. 20 we can write as 4 into 5. So if we are writing 2, 5, 2. 2 into 2, 4. 4 into 5, 20. Then 30. That we can write as 6 into 5. So 6 we can write as 2, 5, 3 in this order. And check once more. 7 into 4, 28. 5 into 5 into 5, 125. 2 into 3, 6 into 3, 18. If you are multiplying here all three, 105. 2 into 2, 4 into 5, 20. 2 into 5, 10 into 3, 30. Same way the next one here. 8. 8 means the prime factors of 8, 2 only. 2 into 2 into 2. So all three columns we can write 2. Next number 105. Same way 3, 5, 7 are the prime factors. 3, 5, 7. Then next number 70. 70 we know that 7 into 10. 10 again we can split as 5 into 2. So 5, 7, 2. We are checking 2 into 3, 6, 6 5s are 30, 2 into 5, 10, into 7, 70, 2 into 7, 14 into 2, 28. Again here 8, 105, 70. You have to rearrange. First you have to find the prime factors and put the correct way. If 5 you wrote it here first and not getting 30, which means you have to shuffle the digits in that row itself. Similarly, we can write the next two columns also the same way. 63 prime factorize first. We will get 9 into 7. So arrange that 3 into 7 into 3. That is 63. If we are taking this way, 3 into 3, 9. 9 into 5, 45. Here 7 3s and into 2, 42, 171. Same way here. 343 when we are prime factorizing that 3 7s are getting. So that we can put straight away there. After 7 check that to get 28. 7 into 4. That 4 we can split as 2 into 2. Same way here. 66 to get 2 into 3 into 11. 66 and 2 into 2 into 11 that is 44.